Oh. Hello, everybody. How's it going? How's it going? Hope you all had a wonderful weekend, a great MLK Day, some would say. Fantastic MLK Day. I figured out soundboards. No need to applause. No need to applause. Yeah, I'm sure right now you're probably cringing because it's probably what I'd be doing. I'm not gonna lie. But we're gonna start here at 6:30. I just want to begin by saying welcome back if you're here. If you liked the last one, or if you like this one, please like the video. It always helps. Hey, there it is. How's it going? I think that's Wes. Love it, Wes. So let's get right into it. So same deal as last time. If you were to go to the YouTube video, let me see if I can find it. Go to the YouTube video. In the description there will be a link. From that link you're going to want to go here to Google Colab. Go to the GitHub. This is as well colab.research.google.com in case you weren't here last time. Go right here, type that URL right in there, select it, and then once you select that, you should see week 2, and now you're in this week's lecture. So let's close that out. So let's begin. Before I import everything, I have a documentation link. You can see the manual, all this stuff, getting started, user guide. So today we're mainly going to be using Pandas, but I imported NumPy just in case. In this episode, yeah, that's right, I'm calling it episodes now, we are going to do a bunch of visualizations. Most of these visualizations are through Matplotlib. You don't have to directly, most of the time, import Matplotlib. That kind of works with Python. So after running this cell, you can see that this contains CSV files. A CSV file, which is a comma-separated value. These comma-separated values allow you to pretty much make an Excel sheet type thing. You can actually import Excel sheets by doing read _ Excel, and then the file, and then you have to choose a sheet. So now that we've done that, you can do URLs. This can be a local or a file on your computer, which I would prefer, but since we're just going to get it from GitHub, this is the data. So let's first of all find some info about this. As you can see, there's 11 columns. What we're trying to guess here is survived, whether or not somebody on the Titanic survived. Now, this is kind of interesting. You get this thing called a P class, which you don't really know what that is. A SIB SP parch ticket. So if you were to go look at the data on what it's about, you can see that their age is just age in years. Sibling is the number of siblings. Parch is the number of parents. Ticket is just the ticket number that person had. Passenger fare, cabin number, port of embarkation. So these here, you can see that these are categories, and you can kind of figure that out because there's only 3 things. There's only 3 places they could have embarked from. And here we see these non-null values, which means that we're going to have to be dealing with null values. We'll deal with those in the next episode. That's right, episode. Got you. And now let's see what the top of this looks like. As you can see, it comes in a table format. Isn't that amazing? That's some big data right there. That's some big data. And if you see, we got the survived column, which is what we're actually trying to guess, and it can only be 0 or 1. The survived has all 189 non-null values, so we know that that's our goal. As a machine learning scientist, we always want to have a goal, something that we could go towards. Let's see. Now we can have, let's describe some of this data. So as you can see, not all of these are being sent, like name, ticket, object, but which ones aren't being put on there? Well, if you look, the ones that are objects are not being put on there because they don't know how to describe it. So things like age, p-class, the number of siblings, the number of parents that somebody has, I think that's what it is. Yeah, number of parents, number of siblings, and the fare. So after describing this, you can see we get a bunch of really cool information, like the standard deviation, the minimum, the maximum, the 25th percentile, the 50th percentile, and the 75th percentile. So right away we can kind of see what's going on here. Hey, Miguel Tejeda, thank you for subscribing. Appreciate it. Okay, now let's go on to Matplotlib. So in Pandas, what we want to do is make this survived column a category, right? So when we have this category, we can do cool things with it, right? I'm actually going to not run this cell, so then we can kind of see how this is going. So there's a lot to unpack here. All right, there's a lot to unpack. As you can see, there's a count gender survived. So basically this right here would be this table, right? And what we're saying is we want to group by sex, and then we want to group by survived, which is giving us this right here. So if we just print this out, so I'm going to add a cell here, this looks like this. It literally just has what sex it was, whether or not they survived, and the count of how many of those that it got. So let's go back. As you can see, after I get that data frame, I can just put the dot plot on there. I can say that I want a bar graph. There's a bunch of different types of ways to plot. Hold on. Let me go to Matplotlib. Here's some examples of charts that you can do, just to start out with. As you can see, I'm barely scratching the surface of it. So yeah, there's so much you can do with this. But for today, what we are doing is we're saying that the X is the column sex, and Y is whether or not they survived. Y is the count of the survived, because that was the last thing that we grouped by. And then here I just changed the color because go Gators. We love the Gators. Hell yeah. Yay! Woo! Go Gators. We love them. And now that we go to here, we can say, instead we can group by sex. We can aggregate the means of people that survived. And now we can say that since they didn't survive as 0 and they survived as 1, that means that 76 or about % of the female population survived, and only about 18% of the males survived. Which is pretty whack. This is real Titanic data, by the way. This is data that was taken many years ago. So as you can see, you're more likely to die if you were a male on the Titanic than if you were a female, which is something we can use later in our models. And today we will be making our first model. Woo! Yay! First model. It's not going to be a neural net, which I'm sure a lot of you are here to learn, but it will get about 95% accuracy, which is pretty good. And it won't be on this data. Yeah, I'm kind of pranking you there. So after we can see like there's more of a chance if you're female that you would survive versus if you were a male, we can separate these into age groups, right? And so we use this function called cut, where we can basically categorize things based off of numbers, right? So we take this series, which is what it is when you call a column on a data frame. So if I would just want to take the type of something here, if you take something, you get a series back if you take a column from a data frame. We can talk about that later if you guys have any questions about that. It's basically just an array with an index. And we separate them into bins. So basically this is the equivalent of saying I'm going to go from 0 to 100 and I'm going to skip 10 every time. So like 0 to 10, 10 to 20, 20 to 30, and so on. And now I'm going to include the lowest, which is true. So I'm going to include 0, which hopefully there's not a person that's 0 years old on the Titanic. But now we can see that the sex is type category and the age range is now a type category, which that is what this cut does, is it converts the float objects into categories. Now what we want to do is we want to plot the age categories, just the size of each age range, and we want to say, you know, how many in each age group are there, right? So it's 10 to 20, you know, 0 to 10, 10 to 20, 20 to 30, 30 to 40, etc. So you can see there's a pretty neat distribution here. By the time we get to 80, 90, there's 0. At this time, when the Titanic was a thing, if you were 90 years old, you were basically dead already. Sorry to say. Whoops. Sorry. But now that we're here, and we can do something that's really cool, right? We can group by survived as well, right? And we can do this thing called unstacking, where if we were to just say this right here, what this would return is something like what we saw before, where you'd have an age range and survived. But if we unstack it, you can see that this turns into something that we can actually like graph, so something that actually works. So 0 and 1 are then separated into their own separate columns, and we can group them and color them, etc. Right? So let's go back. We say stacked is equal to true. This basically, all this does is if this wasn't true, is this would just be right next to each other, which is cool. I like the look of that. And if we did the same thing with unstack and then did this, it would just all be the same color, right? So we don't want that. We want to see who survived, and we want to see what age range they were in, right? So about half of the people in the 30 to 40 age range survived. You can see that a lot of people in this age range survived, but if you were between the ages of 10 and 20, you were probably going to die. Same with 60 and 70. Okay, so now that we've kind of done this, we can see, you know, all these people, they've survived and everything. But what if we also categorized it by the gender or sex? Oh no, that's not good. Rip.
Mission failed. We'll get them next time.
Invalid color, orange, blue. Let me see, what did I do? Why is this not working? Invalid color. Oh, let's try this then. Might not come out as I want it to, but we can give it a shot. So obviously this won't work if you're doing it here. Yeah, okay, so I had it so it was able to do orange and dark blue and everything like that, but I must have screwed something up when I committed to the repo, which, again, happens, you know. It's tough, it happens. Essentially, what you want to do is you want to start saying, you know, whether somebody's male or female. So these two are a group, etc. We have an age range. We can group these all, and we can kind of look over this and see, you know, if you're 20 to 30 and you're a male, there is a very low chance you were going to survive the Titanic. I'm sorry. If you were between 10 and 20, which I know a lot of you guys probably are, I'm sorry, you probably would not have survived the Titanic, which is okay. It's fine. It's fine. Let's see. Wes, how do you change the age groups bins to something that isn't an equal distribution, aka not everything 10, rather a group? So that's a great question. So I'm going to go back up here, and I'm going to basically, instead of range, I'm going to do something like an array or a list. And what you can do is just say 0 and then say 10 and say, if you wanted like 20, 30, 40, 60 like that, you can go like that. Or say you wanted 20, 30, and 40 to all be the same range, right? 50, and then you wanted this to be like up to 80, right? And then this to be like 100. This will do the same type of thing. It'll just be less groups, right? So you can put this in here and it'll be the same thing. But I use range because it's easier to read and I like range. Roasted. Hopefully that answers your question. Sorry it took me so long to answer that. I hope you understand what I was saying. If not, please, if you guys have any questions, please ask them. Now that we are in here, oh, here it is working. Why did it? Okay, whatever. It's fine. It's all good. Now we have 4 colors. Can we get an applause for that? That's amazing. Look at that. Look at how cool this looks. I love it. I love it. So, as you can see, if you are a lighter color, you did not survive. But if you are a darker color, those people did survive. So, yeah, at the top, these people survived. At the bottom, these people didn't. If you're blue, you are male. If you are orange, you're female. So, I really want to know. I hope your legs are okay. My legs are not okay. Wes and I did a leg day today. It was rough, not gonna lie, but I'm here. I'm a trooper. So now that we've kind of done over this, I'm gonna show you guys. So this is something called Seaborn, right? This is kind of a whoa. All right. So Seaborn is a library on top of Matplotlib, which we didn't actually use or import. But what we can do is we can say, well, we did use it. The dot plot is Matplotlib. Okay? And after we import Seaborn, we can kind of get this data set. So this load data set thing, let me open this up real fast. It provides quick access to small number of example data sets. So stuff that we can use that is already in the DataFrame format. They're all .csvs, and you can see all the different types of data that you can retain, that you can get here. I chose iris. There's a bunch of different stuff, like you can try and guess the miles per gallon, car crashes, brain networks, etc., etc. But I chose the iris, which is a data set that holds, well, let's find out. It holds the sepal length, sepal width, petal length, and petal width for each individual species inside of a CSV file or data frame. As you can see, this is a data frame. A data frame is just a series of series, which is hard to explain, but a series is basically just an array with an index, and then a data frame is a bunch of arrays with the same index. So if I describe this, you can see all these were floats, and we can kind of see, how many. There's 150 we have to deal with. The mean sepal length, the standard deviation, all that stuff, all that good data. That data, we love data. Data's the best. Data never lies. And now that we have a bunch of data, let's kind of plot a bar graph, right? So I basically take these and I group by the species, which is an object type, but it automatically, since this is a pre-installed data set, it understands that there's only 3 types that it can be. And those 3 types are Setosa, Versicolor, and Virginica. I have no idea what those look like. Actually, I should probably look that up, but whatever. We don't really care. All we care about is the data. Big data. We love the data. We love the data. Hold on. Data everywhere. I love a good Buzz Lightyear. Love a good Buzz Lightyear. So now we're going to kind of do these with scatter plots, right? So I'm going to say that the x is sepal length and the y is sepal width. If you kind of want to visualize it, the width is basically the x and the y. So basically it fits in this square, and it fits in that square, etc. And what we did to make it change colors is we did this thing called hue. Hue allows you to change the colors in such a way where you can have basically have a categorized column, and each category in that column gives it its own color, right? So this is called a rel plot. I honestly don't know what that stands for. Let's take a look. Yeah, no idea. But that's what Seaborn used. And basically, regular plot, I think. I don't know. But we can basically call this sns.relplot, and we can say that we want x to be our column, and y to be another column, and this hue thing is what I was just talking about, and then what our data is. So it's that easy. You can literally just take any data set and put it onto a scatter plot by just saying which columns you want and the data. The species is a bit of extra credit, which is nice. Now that we're past the rel plot, let's go to a scatter plot, and we can see that the petal length, petal width, etc. It's grouped up a little bit more. You can see, this is, hold on. This is a little bit more grouped up. We can kind of draw a circle around it now, which is what we're looking for. I'll explain why later. And you can kind of see, they're different colors, but it's a little bit more grouped up. Using the petal length. So let's put some of these together, right? If you have these things called facet grids inside of Seaborn, and it basically just allows you to put things next to each other scaled on between the lowest and highest. So it's basically scaled. So you can see, so this is basically a box plot, and then this is the number of occurrences. Okay? Hopefully that makes sense. Does the data love us, though? Unfortunately, the data does love us. It does love us. We love data. Data loves us. It's true. It's true. Big data. Big data is what we need. Right? So instead of it being a facet grid where we have the hue being species, well, the column being species and the hue being species, this basically just changes the color. We don't really need hue here. It'll still be the different species, but I like colors. Colors are great. If we have, say, put these on all the same length, we can see like there's a bunch of these that you can see that Virginica has a longer sepal length. Do I know what a sepal is? No, I do not. do I know what a petal is? Actually, I do. It's the little thing on the flower. And essentially, what we want to do is we want to say that the x is the sepal length, the y is the actual species, so we put them all together, and then we can see them scaled together, which is a little bit easier to tell what's going on here. But if we were to switch the two instead, we can see something like this, which I'm not going to say what that looks like, but you can use your own imagination there. Basically, what we can do is put these together and then have the x be like a category. So that's what a violin plot is for. And again, if we go to SNS, the documentation, which I put a link to, I guess I didn't. Oh, shoot. Hold on. Let me pull that up. That is a RIP. That is what some would call a Windows error. In fact,
mission failed. We'll get them next time.
We'll get them next time, baby. We'll get them next time. Seaborn plots. So basically, we can go in here. We can see all the different types of seaborne stuff we can do. Again, if you're ever looking for a type of graph, it's probably been made before. I promise you, it's probably been made before. Just try and look it up. You know, we aren't geniuses. We're just we're Google fanatics. We love Google. Google's the best. Thank you, Google. A sepal. Yes, I have no idea what a sepal is, but hopefully somebody knows. If you know what a sepal is, please let me know. In fact, if you even want to look that up on Google, it could be a little practice. Let me know in chat. So now that we've talked about the different types of plots, which you can go in here and you can kind of see, like we got violin plot, box plot, cat plot, all these types of plots, distribution plot, heat map, his plot, etc. We aren't really going to talk about those because, you know, I'm just here to just show you guys some cool stuff. But basically, what we have here is called a joint plot, right? What this is a KDE. Again, I'm honestly uncertain what a KDE stands for. But what it does is it allows you to find the distributions of where all the points are in a given graph. So if we put the sepal length and sepal width in here, we can kind of see where the distribution is, and you're able to kind of view this circle of where all these are. So if you want to think about this, it's kind of like an elevation plot, right? The more dense the lines are, the more sort of altitude it is. So if you were to look at this like a 3D graph, right? Having something where there's like the Y is the Z is the count, right? You can go up and yeah, nobody really cares. So I'm just going to continue. I'm just going to we'll get him next time. We'll get him next time. Basically, what we can do is visualize these plots and figure out, you know, how many counts are of each value, how many where each value specifically is, and then that utilizes the standard deviation as a radius. I believe it does. You can look up more on KDE here. KDE plot. It looks like it's the kernel density estimate. Again, Google is your friend. Yeah, so if you want to learn more about that, I would suggest StatQuest. That's not my job. That's not my job. My job is to show you guys some tools. If you guys actually have any questions on KDE later, please let me know. Yeah, I got lost in the sepals. It's unfortunate. It happens. It happens. But now we talk about some joint plots, which I use a lot personally to see different things. Now we can talk about pair plots. So this is a cool graph, isn't it? So basically, this is just every plot that we had before, but it takes every single column in the data frame, and so sepal length is just the count for each one. This is sepal length and sepal width together, which we already did. But if we want petal length and sepal length together, you can see these are grouped really well. And you can kind of see sepal width and petal length, petal width and sepal width, and they're changed. Their color kind of changes, and you can see how things kind of group up, right? So we can do these. All we have to do is just change the kind. So this kind is scatter, and what we do basically is we say everything off the dialog is a scatter plot. S is equal to 35. That just means the size of the actual, like what the thing looks like, and the alpha is just how. So if I were to change this to say 0.5, this would be these dots. If you go in a little bit further, they're only half filled in. They're kind of opaque, but I like 0.9 because 0.9, See, now we can go back here, and now they're fully filled in. Okay, so we can do the same thing with KDE, right? Or the kernel density estimate. Very nice, very nice. And now we can see all the KDE graphs for every single permutation of all the columns, which is great. We love saying that. I reluctantly redact my conclusion. Google as a normal human. Yes, indeed. So essentially, what we need to do is we can kind of see more groupings. These just kind of show you the density of where these are falling, and you can see the counts. You can see like so petal length. Like there's more petal length for a setosa here than in between 0 and 2. There's a bunch of these between 0, 2, and 6, and then more of these between 4 and 8, which is really cool. We can kind of see how they kind of group up. This is a histogram, so you can kind of see, you know, the darker it is, the more there are, etc., etc. And these all are kind of self-explanatory. You connect each X and Y. You can figure out what each one's doing. And then let's go to here. So what this does is we take plot2. So we make this variable and we put plot2 into it, right? And we add this pair plot, right? So what we can do is we can say that here's the species, kind of, scatter, yada. We kind of went already over that. But what we haven't gone over is this dot map lower. So in the dot map lower, what it does is it overlays a KDE plot or whatever you put in here on top of the scatter plot, which looks really cool. Yeah, I know. Data science is all about looking cool. And it's, wait, hold on. Pulling it up. Data. We love data. Data's the best. So now that we've kind of gone over how to graph some stuff, and I've gone over joint plots, pair plots, and everything, let's make our first model. So what we have to do is, so we have 150, I think, 150 different things inside of our database. Yeah, none of them are null, which is good. And what we can do is we can use this full data set to create a training set and a testing set. Now, if you have a neural network, you have a training set validation set, which the neural network uses to validate itself while training. And then you have a testing set for after to determine your accuracy or metrics. And so we need to generate the train and test from our data set, right? So we use this function called train test split, which I put the documentation on there for that one. You can see we can just put these two arrays in here, the X and the Y. So the X is what we want to, is what we have, like the information we want to give the computer, and then the Y is the information we want the computer to give back. And so there's normally you'll have Y train, Y test, sort of X train, X test. X val you don't really use that much unless we get to really high up stuff. But essentially, we can create this test size. Normally it's standard to go around 30% test size and 70% the normal size, but you can change it to whatever you want. For now, we're going to go with 70. What we're going to do is we're going to create these X train and X test data sets. What this basically does is it splits all of our data, and so now instead of a X underscore train dot shape, so now there's only 105 rows inside of this data set. And then this is going to be, 45. So as you can see, it's split into 30%, 70%. And now we can do this thing called a random forest classifier. Now, what is a random forest classifier? I have some pictures for you guys. So a random forest is basically a forest of decision trees. And what is a decision tree, you guys ask? Well, a decision tree is a way for an AI to decide a sort of, is there a theoretical best size percent for the test set compared to the total set, or is it just 30% is industry standard? So normally 30% is the industry standard. It really depends on your data set. So if you have something like GPT-3, where your data set is huge and you want your sort of AI to have a bunch of not as much training data as it is test data, and you have a really large test set, and you want it to be really, really accurate. If you want, the more accurate you need it is the higher tests you need, essentially. So it's kind of like school, you know. If the more you test it, the more accurate it's going to be. So what is a decision tree? A decision tree is a way for a computer to follow a set of rules that are put into a guidelines using Gini coefficients, stats, and everything. We basically just blame the algorithm if something comes off. I personally won't be making any of these ourselves. Sort of any of these algorithms from scratch. I will be using Python libraries, just like a normal human being. I'm not an absolute Chad at programming. I'm just a normal human being. And we can basically just create this random forest classifier with a max depth, which we'll talk about later. Random classifier is random estimator. So there's a couple problems with the random forest classifier. It's hard to retrain a random forest. So if you have something like a neural network and you wanted to add different classifications to it, you can't do that with a random forest classifier. Whatever it classifies is the entire set. If you wanted to add, say, a new species to our set, you couldn't do that. You'd have to retrain it entirely. Something like a neural network, you could just add the species in, which we will talk about later. But with a random forest classifier, there are limitations. However, it is a good first model to learn. Essentially, now we can create these predictions where we just take the prediction and we predict based off of the test. So the test only has sepal length, sepal width, petal height, and this is data that the computer has never seen before. And it is able to get 95.5 repeated percent accuracy, which is wild. It's able to tell the species of flower based off of the sepal length, sepal width, petal length, and petal width. It is able to tell the species of the flower with 95.5% accuracy. Wild. Wild. That is what I like to call data. You're about to go into a big, great world of data, and you're going to learn how to use it. You're going to love seeing DataFrames. I can already tell. I love it. You guys are going to love it too. So what did we get wrong? So Bing Bong, there's a new method, enumerate. Enumerate allows you to say that you have an index I and the actual thing that's in that index you want to put right after a comma. This allows you to get the index and the actual data that's there. Very useful. We'll be using that later. Wanted to put that out there. But we basically only got two wrong. One of them thought it was a versicolor when it was actually virginica, and one of them thought it was virginica when it was actually versicolor. right? So what this does is it goes through each of these, says if this prediction is not equal to what we have in our testing data set, if the prediction is not equal to what it should have been, I'm just going to print out what it should have been and our prediction, right? So that easy. You just go through, you figure out what you got wrong, and then we have this thing called a confusion matrix. A confusion matrix allows you to see this data in a matrix type format. So as you can see, it guess this, the Y's is the actual, or this, so this is Virginica, versicolor, etc. These, it got 18, all 18 right for the, what's the first one? Setosa. It got 15 out of 16 right for the Virginica, and it got 1, and it got 10 out of 11 right for versicolor. And this is data that it has never seen before. We love seeing that. It's beautiful. And that is your first model. Hopefully you guys enjoyed. There really isn't much else for me to do or talk about. Hopefully you guys have questions, because I went real fast on this. And yeah, hopefully you enjoyed. Thank you all for coming. It was great. I love making this stuff. Yeah. If you guys have any questions, let me know. I will be in here, just sitting, waiting. Those are some mighty fine numbers. In fact, 95% accuracy is scientifically significant, which we can do. Of course, Jordan, thank you for coming. I appreciate anybody that comes by. If you guys have any suggestions for how to improve, please let me know. I'm just trying to make this as great for you guys, as easy to understand for you guys as I can. Okay, how would you go about improving the accuracy from here now, knowing these errors? So ways you can improve the accuracy is actually pretty wild. So what I would do is figure out a way, like here. If I'm a thinking man, you know, I got my multi-monitor chat out, thinking about graphs. Look at this graph. If I'm looking at these graphs, what can I do? You know, how can I make this a little bit better? Miguel, where can we find the fundamentals where this builds also off of? So I will put you guys to this man called StatQuest. Wes, I will get to your question in a minute. This guy called StatQuest talks about this all in depth. And so if I were to go search StatQuest.
I'm Josh Stormer.
Hello, Josh. You can go in here, and if you wanted to learn a lot more about, say, random forest, he goes way in depth about how these random forest works, like how to find the Gini coefficient, how to do exactly what you would probably need to do in order to implement this yourself in Python. Again, I'm just here to show you guys some tools, show you guys how it works, but essentially he goes over it. I would suggest you do decision trees first, because random forest trees are essentially just a series of decision trees, which I actually have a picture for. Hold on. So a random forest classifier basically is just a thing where you have n features, and each tree outputs a certain class or classifier. So in this case, these classes would be the what species it is. And what it does is it takes the majority voting and it creates a final class, right? So it takes this, each tree has a vote. It randomly weights those votes, and then it creates this thing called majority voting, and it outputs a class. All right. If you want to see how it makes these trees, I would suggest you go watch the StatQuest video. But it has a lot to do with stats, something like a Gini coefficient or a standard deviations and all that stuff. There's a bunch of rules for how they're generated. All right, so back to the question that Wes was asking me. All right, Wes, so if I were to want to make this more efficient, what I would do is loop through here. If I wanted to make this more accurate, what I would do is I would, just with random forest classifiers, I'm not going to show you guys anything else for right now, but if I wanted to go and make, say, in range like 0 to like 1 to 10, so if I wanted to loop through this range 1 through 10, and I wanted to get I would just say max depth I. So what this I does is it gives you a max depth for how far each tree can go. And what you basically would want to find, right, is you would want to find what the best depth is for your predictions. Again, but there's something also that you don't want to do, which is called overfitting. Overfitting is not good. When you overfit, which you can easily do with a random forest tree, it means that you've kind of gotten too accurate based off of the training set. What you want to do to remedy this problem is to kind of graph out things as you're doing it. You know, if you're doing way too high of a depth, there's literally no reason for you to do something like that. But now, just for sake, I can basically take what I've been doing for this here and get all this accuracy score and everything. And then I can say accuracy, and then if you guys watched the last video, you know what a formatted string is. Accuracy with an I depth, and I can say for each depth it's going to have a certain accuracy, right? So as you can see, with a depth of 1, it's actually really good. With a depth of 2, it's about 95%, and so on. So it seems like these ones we get wrong are really just outliers, and you can kind of go like that. Of course, Miguel, thanks for joining in. And yeah, so basically what you can do is just run and maximize your random forest classifier and find which one has the best model. Actually, here would be probably 1 depth. I did 2 depth. Again, it's just arbitrary. We aren't actually going to use this unless you're planning on going out and finding a flower. Hold on. Finding a flower like this. Let me look up a setosa. Unless you go outside, find a setosa like this little guy here, and you want to take a measuring tape and really take the petal width and the petal length and really get real deep in there and find yourself a classifier. But what we're going to be talking about later is ways that you can just take a picture of this, and using things called convolutions, neural networks, we can predict what species the flower is based off of a photo, for example, which is going to be a really cool lecture. We probably won't be doing flowers specifically. We'll probably be doing dog species, cat species, something else like that. But Jordan, how can you tell if overfitting is a problem for your model? So the way you can tell overfitting is a problem for your model is if, say, you have something like this, right? Where you can kind of see, like, it's not taking your training set and using it exactly. It's not trying to so basically, you don't want it to be exactly like your data set. So like if you were to have something like a point here per se, it would be really close on this model, but something like this would be really far away for certain points, but really close for your training set. We can kind of see how this kind of comes into play by looking at, let me see, training accuracy. Let me see if there's a graph I can find. I was not ready for this question, but it's a great question. Thank you for asking it. So what happens is, so over time, your set's going to kind of look like this, right? You'll have a training set accuracy, which will keep going up. No matter what happens, your training set accuracy is going to keep going up if you keep adding, say, levels or something like that. But when your test set accuracy, so when your test set starts going down, that's when you know you are overfitting. And what you want to do is you kind of want to find the peak of your test set accuracy, and you can. We'll go over this. We're going to learn a tool called weights and biases that actually keeps track of all this stuff, and you can see what your different epochs are and everything. But essentially, when you know you're overfitting when your test set accuracy is going down after each epoch, or after you keep training it. So hopefully that makes sense. Thank you for asking that question. That was a great question. Yes. As well, nice. Awesome. All right, so hopefully you guys like some of the stuff that I was coming up with. Today is Martin Luther King Day, and I just wanted to share some of my quotes from Martin Luther King I had written down. Let me see. Forgiveness is not an occasional act. It is a permanent attitude. Right? You can't forgive somebody once. You have to forgive them forever. That is something. Love me some Martin Luther King quotes. He had a great life. He unfortunately died too early, and I hope that he had a great. I hope his family's doing well, and I hope that the message that he had lives on. It was a great message, and I'm glad he deserves his own day. Yes, Jordan, that is deep. I agree. Hashtag deep. Indeed. Hold on, let's all give a round of applause for Martin Luther King. Man's a legend, absolute legend. I encourage you guys to get out of your seats. Give a round of applause. Man is a beast, absolute legend. All right. Is there anything else you guys have questions on? Let me just say some more quotes while you guys are in here. Let's see. You want to see the dumpy? I don't know. This is an educational broadcast. But I mean, if you want to see the dumpy, I'm joking. Love you, Wes. Love you. Jordan, thank you for coming by. I appreciate anybody that comes in to watch these. I put a lot of work into these, and I hope you have a great day. Please honor Martin Luther King and what he did for this country. Man was a legend. No. So let's start watching the StatQuest video. Let me just get this guy right up in here. Search here. We go bye, COS. Thanks for coming by. Appreciate
it's easy
you.
to build a tree from numeric data. If a person has a really high resting heart rate, then that person had better see a doctor. And if a person does not have a super high resting heart rate,
Again, StatQuest,
then that person is doing okay. Here's one more simple decision tree.
Hopefully I don't get DMCA strikes.
This
That would
decision
suck.
tree is based on ranked
That'd be a
data.
brub
One
for
is super
sure.
hungry, and 2 is moderately hungry. If a person is super hungry, they need to eat. And if a person is moderately hungry, they just need a snack.
Yes.
And if they are not hungry at all, circulation and blocked artery status to predict whether or not a patient has heart disease. The first thing we want to know is whether chest pain, good blood circulation, or blocked arteries should be at the very top of our tree.
Yes.
We start.
So these all can be decided by a correlation matrix. You can tell what to choose based off of what is correlated best with each value. Yeah, so that's pretty cool. That's pretty neat.
Should be at the very top of our tree. We start by looking at how well chest pain alone predicts heart disease.
Yeah, see, so he's going through and he's finding each, which one is most correlated, which column has the highest.
Here's a little tree that only takes chest pain into account. The first patient does not have chest pain and does not have heart disease. And we keep track of that here. The second patient has chest pain and heart disease.
Any questions?
And we keep track of that here.
Let me at it.
The third patient has chest pain but does not have heart disease. The fourth patient has chest pain and heart disease. Ultimately, we look at chest pain and heart disease for all 303 patients in this study. Now we do the exact same thing for good blood circulation.
We love it.
Lastly, we look at how blocked arteries separates the patients with and without heart disease. Since we don't know if this patient had blocked arteries or not,
Thank you guys for joining.
However, there are alternatives that I'll discuss in a follow-up video. Remember, the goal is to decide whether chest pain, good blood circulation, or blocked arteries should be the first thing in our decision tree, aka,
in fact, I'm going to post this in the chat,
the root node. So we looked at how well chest pain separated patients with and without heart disease. It did okay, but wasn't perfect. Most of the patients with heart disease ended up in this leaf node. And most of the patients without heart disease ended up in this leaf node. Then we looked at how well good blood circulation separated patients with and without heart disease. It wasn't perfect either. Lastly, we looked at how well blocked arteries separated patients with and without heart disease. Note, the total number of patients with heart disease is different for chest pain, good blood circulation, and blocked arteries, because some patients had measurements for chest pain, but not for blocked arteries, etc. Oh no, it's another one of those ghastly jargon alerts.
All right.
Because none of the...
I actually decided that we should go over this. Some of these this Kaggle. So what is Kaggle? Kaggle is a place where you can go find a bunch of data sets, right? You can go find, police locals, NBA tattoos, nutrition studies, NFL predictions, Omicron things. You can go see some competitions. The one we're going to be working on here is the Titanic machine, but you can have digit recognizers, house prices, feedback, future sales, tabular. It's just a bunch of that data we were talking about. We love data. Data is the best. That's a very big theme inside of this course, or I guess you could call it a course. It's a very big theme. This is where I go to find a lot of my data. Go practice, find a bunch of competitions and stuff that I can go and compete with. You can also see other people's code and how they do it. As you can see, the Titanic is used for random forest, feature engineering, tidy models, spiral prediction, all this stuff. You can sort by Python, visualizations, all this stuff, but yeah, there's so much data, almost way too much for anybody to count. As you can see, not a lot of people actually end up using this, but I think it's a great resource and everybody should use it. We have one more minute. Next week we are going to talk about how to use a random forest and other types of classifiers in using the Titanic data set that we started with today. We're going to start by cleaning it, visualize some data, and then we're going to create, hopefully, our first neural network. I want all you guys to come here and make your own classifiers, use your own brain, find your own stuff on Google, and submit it later. And if you guys have something to submit, send it in the Discord or over email. If you want my email, let me know. And I will certainly show it to the rest of the class. And there is a participation grade. Yeah, that's right. You're getting graded now. Get roasted. You're getting graded. So you will need to participate because that'll make it so much better for everybody. I appreciate everybody that came to this. I will see you next Monday at 6:30. Bye.